Welcome to this HP Expert One presentation. This is the third video discussing IP routing. In previous videos, we looked at the basics of IP routing and discussed distance vector routing protocols. In this video, we're going to introduce link state routing protocols and look at some of the advantages of link state routing protocols. Let's get started. Link state routing protocols have greater visibility of the network and are generally more powerful. So as an example, OSPF is a more powerful routing protocol than RIP. Link state routing protocols, to use an analogy once again, have a roadmap of the entire network and can thus make better routing decisions than distance vector routing protocols, which only see a single sign. So rather than just viewing a sign saying turn left and the city that you want to drive to is 100 miles away, the router has a roadmap and thus has better visibility of the network or the topology. Link state routing protocols will flood the network with what are called LSAs or link state advertisements. This information is flooded through the entire network if the routers are configured in a single area, or are flooded within the area when special areas are created. Thus, information about the entire network or the area is received by all routers within that network or area. The LSAs are propagated between all routers without a change. All routers will individually create or populate what's called a topological database, which is a database that's the same on all routers within that area, or once again, if running only a single area, all routers within the network. That topological database contains information about all routers within that area or network, all the links connected to those routers, and the states of those links. Hence the term link state routing protocol. Is the link up or is the link down? So router 1, as an example, would tell all routers within the area about the links connected to it and the state of those links. Are they up? Are they down? The routers run what's called the shortest path first algorithm, or OSPF algorithm. OSPF, as an example, is open shortest path first. In other words, it's an open standard that runs the SPF algorithm. When the routers run the SPF algorithm, they put themselves at the root of an SPF tree and then calculate or work out the best route to destination networks from their perspective. Routers' perspectives will vary depending on where they are in the network, and thus the best route for one router may be different to the best route for another router. They essentially determine the best route for themselves by running the SPF algorithm against the topological database, and then they put the best routes into the routing table. Examples, once again, of link state routing protocols include OSPF, or Open Shortest Path First, and ISIS, or Intermediate System. Link state routing protocols, such as OSPF, allow for the division of large autonomous systems into smaller groupings called areas. In this example, we have a RIP router connected to a router running both RIP and OSPF. So RIP is connected to the OSPF autonomous system. The routers within OSPF are under a common administrative domain. In other words, they are part of the same autonomous system. The OSPF autonomous system, however, can be broken up into multiple areas to allow for smaller routing tables, reduction of flooding of link state advertisements, summarization, and more efficient use of resources. If you have many routers in a single area, the routing tables of those routers can get very large. So this allows for the reduction of routing tables on certain routers by breaking the autonomous system into a hierarchical design with multiple areas. In OSPF, these routers are known as area border routers. They have interfaces in multiple areas. These routers are known as internal routers. They are internal to an area. This router is known as an autonomous system border router. It connects OSPF to an external autonomous system or routing process, in this case RIP. These routers are known as backbone routers, and they are also internal to the backbone area. One of the advantages of creating multiple areas is that link changes within one area are hidden from other routers in other areas. So it's possible within OSPF that if a network 10110, which is in area 1, goes down, that information is hidden from routers in other areas. So the router in area 2 and the router in area 3 will not be aware that network 10110 has gone down. This can be done by creating special areas known as stub or totally stubby areas and using route summarization. The idea is to use your resources more efficiently by reducing the flooding of LSAs. Link state advertisements within area 1 can be contained within that area, and summary LSAs are propagated into other areas. Those LSAs can then be blocked by the ABR so they don't go into other areas. So routers in area 2 are unaware of specific routes in area 1. To enable connectivity, a summary route or default route can be propagated into area 2. Some of the benefits of link state routing is firstly fast convergence. Changes are reported immediately, and link state routing protocols tend to converge a lot quicker than distance vector routing protocols. Link state routing protocols are more robust as the routers know the full topology of the network or the area. They tend to be less susceptible to routing loops because of their greater visibility of the network. Routers know the topology and can thus work out the best route to every destination. Link state packets are sequenced and acknowledged within OSPF. So if an update is not received by a router, it's retransmitted. RIP does not form neighbor relationships or peer relationships. OSPF does. So if an update is sent from one peer to another and the peer doesn't respond, the update can be retransmitted. The hierarchical design of OSPF and other link state routing protocols optimizes resources. It allows for smaller routing tables because of summarization and fewer shortest path first calculations because of address hiding. Essentially, if the network is designed properly, certain routers will have far smaller routing tables and will do less calculations. Routers in area 1, as an example, will not be aware of all of the routes in area 2 or area 3 because of the use of summarization on the area border routers and the configuration of special areas such as stub areas. The hierarchical design also allows link state routing protocols to scale to much larger environments than distance vector routing protocols. Large ISPs on the internet, for example, will run OSPF or ISIS internally within their autonomous system because of the scalability of this routing protocol. There are, however, some drawbacks to this routing protocol. The first one is that there's greater demand for resources on routers and switches. More memory is required. The routers have multiple tables. As an example, they'll have a peer table or neighbor table. They have a topology table or link state database. And they have a routing table. More memory is required to hold multiple tables. There's more demand on the CPU. The Dijkstra's algorithm can be very processor intensive. Link state routing protocols also require strict designs. In OSPF, as an example, area 0 is always required when you have multiple areas. All other areas have to touch the backbone area. All traffic from area 1 to area 2 would have to traverse the backbone area. The configuration of OSPF can be more complex than distance vector routing protocols such as RIP. However, the advantages of link state routing protocols generally far outweigh the disadvantages, especially in a large environment. Thus, in large topologies, OSPF is seen as a better choice than RIP. That concludes this video looking at the basics of routing. In this video, we discussed terms such as autonomous system. interior gateway protocols or IGPs, exterior gateway protocols or EGPs. We looked at the difference between distance vector and link state routing protocols. We discussed classful and classless routing protocols. For more information, please visit hp.com/go/expert1.